Good morning, class. We are looking at chapter 3, differentiation rules, and this section is about derivatives of trig functions. So we covered a couple of basic sections, such as dealing with derivatives of polynomials, exponential functions, product and quotient rule. And now we are going to move on to trigonometric functions. All right. We've already discussed, in essence, their derivatives, but we really have to look at, in essence, the proof of that. Before I do that, a couple of things I want to mention on this page, class. The new stuff, if you will. Okay. The limit of sine theta over theta as theta approaches 0 is 1. We're going to go over the proof of that. We need this to prove the derivative of sine is cosine. The limit of cosine theta minus 1 over theta as theta approaches 0 is 0. I hope you realize both cases, they give us 0 over 0, and then they require the proof. This is all the stuff, definitions, okay? This is the product and quotient rule, the sum and difference rules over here, the constant, the power rule, exponential rule, and now these are the rules for trigonometric functions. So let's quickly recap. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant x tan x. And the derivative of cosecant x is minus cosecant x cotangent x. So let's look at some proofs here. Okay. All right. What I want you to see, okay, a couple of things. Starting from the left side, everybody remembers the unit circle. This is the unit circle, x squared plus y squared equals 1. If you graph a unit circle, okay, so let me just quickly graph it here. This is the unit circle, where this is 1, 0, this is 0, 1, and so on and so on. Now, if you look at this part, this one, class, is just this quadrant. The first quadrant is shown here, okay? So this is a unit circle. It's a portion of it because we are interested in this quadrant. And every pair has coordinates x comma y. X is represented by cosine theta and y is represented by sine theta. I need this space, so I'm going to erase that, okay, class? Okay, I'm going to erase that, but that was a unit circle, okay, not a big deal. Now, what happens with the unit circle? Okay, let me give you the synopsis of the proof and then we look at it with more details. So first, the unit circle. Now, if you look at this portion of it, this is theta. OB is the radius and it's equal to 1. OA is the radius and it's equal to 1. And AB is the arc opposite the theta, okay? So what we want you to see is very simple. The sine of theta is this perpendicular line segment BC over the hypotenuse 1, so it becomes BC. So BC itself represents the sine. Again, I'm giving you the synopsis, but we'll look at it with more details. Just pay attention, make sure you get this. So BC represents the sine. AB is the hypotenuse of this triangle, and it's larger than BC. And this AB is the arc, and it's larger than this AB, which is a line. This arc is the same as theta because this is a central angle. So BC represents the sine theta, and it's smaller than arc AB, which is the theta. So sine theta is less than theta. And this arc, if you combine AE and EB, the arc is less than that. Okay. And EB is less than ED because in this triangle, ED is the hypotenuse. In other words, the arc AB is smaller than this line AD. Okay, class? So let's quickly recap. BC represents sine theta. Arc AB represents the theta. Okay. And what about AD? That is the tangent theta. Why is that? Tangent is the opposite AD over OA. So we are saying the sine is less than theta is less than tan theta. And we're going to use that concept. So theta is less than tan theta. I showed you in that triangle. Sine theta is less than theta. Okay, these are the two that we are going to combine. So I went over this arc AB and how arc AB ends up being less than this line segment AD. This is the synopsis of that. And therefore, arc AB is less than tan theta, and so theta is less than tan theta, and we know tan is sine over cos. Now, how do we get there? We can multiply this, okay, by cosine, okay. And so cosine theta, okay, is less than sine theta divided by theta. What are we doing? We can multiply both sides by a positive value. Remember, the sign will flip over if you multiply by negative. But remember, we are in the first quadrant. Everything is positive. Theta is positive. Sine is positive. Cosine is. Everything with regards to the first quadrant is positive. So if I multiply both sides by cosine, I get cosine theta on this side, cosine theta times theta less than sine. If I divide by theta, I get to this one. Okay. Let me just explain number two. Do I have to write this? Yeah, maybe I should write this quickly. Let me put for you over here. We can say if we multiply this one by cosine, we get cosine theta times theta less than sine theta. And then if you divide both sides by cosine, by theta, you get cosine theta less than sine theta over theta. Anyways, the other part, again, I had explained it, so I'm going to quickly recap. Why sine theta is less than theta? Remember, sine theta is represented by BC. That's why. Theta is represented by the arc AB, and that's all there is to it. Okay, so you show that, so you can see the step by step and the explanation that I gave you. So sine theta is less than theta. Okay, so we have this. We're going to divide both sides by theta. So sine theta over theta becomes less than 1. Okay. We put number 1 and number 2 together. Cosine theta is less than sine theta over theta, and it's less than 1. We put 1 and 2 together. Okay, and then what happens? Now we're going to take the limit of both sides as theta approaches 0. One side, 1, 2, 3. There are 3 sides. We take this one and this one. Both of them go to 1. And by squeeze theorem, the middle term happen to be the same. So limit of theta approaching 0 when it's 1. So this one gives us 1. Cosine, everybody knows cosine of 0 is 1. Okay. So by the squeeze theorem, the limit of sine theta over theta as theta approaches 0 equals 1. I'm not going to expect you to do this proof for me, but if you can follow it, it is truly helpful. Okay, everybody? If you can follow it, it is truly helpful. All right. Now let's put this to good use. Let's use this. Okay. This has a lot of trigonometry and geometry involved. Trigonometry and geometry involved. So having said that, let's go to the next one. So we just proved this one. Now we want to prove this one. Okay. And to prove this one, we use a trick. The trick involves the conjugate of the numerator. Obviously, everybody can see if we plug in, we get 0 over 0. Let's multiply by the conjugate. Needless to say, the parentheses in blue is equal to 1 because we are multiplying the top and the bottom by the same. All right. So what happens when you multiply the top, you get cosine squared minus 1. And everybody remembers sine squared plus cosine squared is 1, right, class? Now, when we know this, that means sine squared is 1 minus cosine squared is equal to 1 minus sine squared, and cosine squared theta minus 1 is negative sine squared, okay, class? Negative sine squared. So let's see what we do now. We cut this using the limit clause into 3 pieces. We take the negative out, and the numerator, we're going to say sine times sine, and the denominator is theta times the parentheses. So take a look, we make up 3 pieces. Negative sine, sine over theta, and sine over cosine theta plus 1. Okay, the negative remains. Limit for this part times limit for this part. Okay, we're using the limit clause. This we already know it's equal to 1. This is 1. What about this one? Let's plug in. The top becomes 0, the bottom becomes 1 plus 1, which is 2. 0 over 2 is 0. 0 times any number is 0. I hope everybody is comfortable with this, okay, class? So we are looking at some proofs, and that requires knowledge of trigonometry. As we come across it, I give you the formulas you need, okay? And since we are added right on this page, let me add a couple more because it's coming up. What you're looking at, this is Pythagorean identities, because I'm going to put more than one now. Okay. If you divide both sides by cosine squared, what do we get? Tan squared plus 1 equals secant squared. If we divide, again, I'm looking at number 1. This is number 2 and number 3. If I divide number 1 by sine squared, both sides, I get 1 plus cotangent squared equals cosecant squared. These are all called Pythagorean identities. You need them. Okay, class? Pythagorean identity. All right. So f of x is sine, f prime is cosine. Let's prove that one. So let's look at the proof. Well, we are going to stick with the definition. So when you plug it into the definition, you get the limit as h approaches 0 of sine x plus h minus sine x over h, and you got to use that one. So I'm going to remind you of sine of alpha plus beta. Okay, let's see where we can write this. Sine of alpha plus beta. Anybody remembers that? What is sine of alpha plus beta? Class? Sine alpha cosine beta plus cosine alpha sine beta. Okay. So you need to remember this, class. We will look at cosine also in a moment. But anyways, so that becomes sine x cosine h plus cosine x sine h minus sine x over h as h approaches 0. So I hope you see where it comes from. It simply comes from this sine of sum, okay? All right, we are going to put the first and the last together, those two class, this one and this one together. And as you can see, sine x can be factored out. So the first and the last one. Sine x can be factored out. When we look at the first fraction, sine x can be factored out, as I mentioned. So let's do that. When we do that, we can write it in this fashion. I hope you see that if I put the h under a large fraction bar and sine x is at top or sine x is out, makes absolutely no difference whatsoever. Why are we doing this? Well, recall. By limit laws, we can cut them into two pieces. We separate the sine and we separate the parentheses. We separate the cosine and we separate the parentheses. Now, let's see what happens here. Okay, sine x becomes sine x. But what about this one? I hope you remember. It was 0. What about this one? Limit of cosine x as h approaches 0, that's cosine x, because it just pertains to h. And this is 1. Okay, look at the limits that we have here. And using the same limits, okay, this class, this one is this one. You're changing the theta to h, big deal. And the first one is this one, you're changing the theta to h. I hope you realize it's really not that big of a deal, class. We are dealing with absolutely the same thing, okay? And that's it, okay? Therefore, the final answer is cosine x. Believe it or not, this is the proof, class. Okay, this is the proof. Again, we are looking at some proofs just to make sure we are in good shape. And as you can see, there is a lot of trigonometric identities that you're supposed to know. Everything that you're supposed to know, I will refresh your memory, but after that, you are on your own to make sure you remember. Okay, class? All right. Now, if we look at graphs, what graphs? Graphs of sine and cosine. Graphs of sine and cosine. And when we learned how to graph the derivative function, that is really helpful. Just as an example, let's just look at, if you look at this part, this corresponds to 0, this corresponds to 0, this corresponds to 0. So if you look at this, just this part, what is this? This part is increasing. You just write. So if you're looking at this part, what's going on? Increasing, f prime is above the x-axis. At this point corresponds to 0. At this point corresponds to 0. And in between has to be above the x-axis. I hope you see that. Never mind the rest. Just look at this piece. And then the rest, you can utilize them in the same manner. So increasing f prime is positive, and where is the tangent line horizontal? F prime becomes 0. Okay, it's pretty straightforward. And therefore, of course, this is the function everybody is familiar with. F prime of x equals cosine x. You know this is the graph of cosine, right, class? All right. Having said that, let's look at the proof for cosine, everybody. Let's look at the proof for cosine. Again, we are going to look at the definition and use that. So we are going to plug in and we get cosine of x plus h at top minus cosine x over h. That is the limit that we need to look at. Now, what is cosine of alpha plus beta? Cosine alpha, cosine beta, minus sine alpha, sine beta. So we are going to apply this, okay. But instead of alpha and beta, we have x and h. Okay, class? Again, we are going to put the first and the last one together and factor out the cosine x. The first one, the last one, we put them together and we factor out the cosine x. So we have this part and then this part. We separate it into two fractions. As we separate them, please understand I can put cosine x at top or just in front of a fraction bar like that, makes no difference. Why are we doing this? Okay. Why are we doing this? It's very simple. Okay. Because we want to make sure we get to the result we want. Okay, we are separating it in this fashion. And now everybody remembers this limit is what? 0, right? This whole thing goes to 0 because this is cosine, okay? And in this case, this is 1, so you get only this one, which happened to be sine with a negative in front. Okay, everybody. So I hope everybody is clear. as to what's going on. So we just proved that if f of x is cosine x, f prime of x is negative sine x. So we went over the proof of that for everybody. Okay. Now let's look at some examples, class. Okay. Let's start with easy questions to get us started. We want to differentiate this. Obviously, we remember the formulas here. Okay. So we're going to use sine, cosine, you name it. Sine. So what's the answer to part A? What do you think, class? Anybody? And you can use this. Anyone? The derivative of sine is cosine plus pi times the derivative of cosine is negative sine. So in one shot, we can say y prime is cosine t minus pi sine t. Okay. All right. Let's look at the next one. The very first thing we need to do, we need to change the fourth root of t to t to the power of 1/4. Therefore, the power rule can be used. Okay, everybody? The power rule can be used. And so, with that being the case, the first one becomes an easy case of 1/4 t to the power of 1/4 minus 1. The second one is just itself. The third one, minus 1/2 cosine t. So if you have to rewrite it, notice is negative 1/2 cosine t. So it's negative 1/2. Cosine gives you negative sine, so it ends up being positive. So I hope you see that. And this is the only calculus step, and we are done. We just rewrite it because 1/4 minus 1 is negative 3/4, goes down, becomes positive 3/4, and you can rewrite it in this fashion. I want to make sure everybody understands what's going on here. This is negative 3/4. If you take it down, becomes positive 3/4. And writing it in proper format would give you the answer that you have here. Okay. Okay, class. So having said that, let's look at this example, y equals x squared sine x. And I hope you see that you are using product. So I'm going to put a raised dot between the two just to make sure we understand what's going on. And to refresh your memory, the formula was f prime g plus g prime f. This was a shorthand notation. So if the first piece is f x squared, it becomes 2x times sine x, and the second one is sine becomes cosine times x. And you just make sure you put this in front, class, okay? Because otherwise it's awkward. One may think it's cosine of x cubed. I've seen students making that mistake. We don't want to take that chance, okay, everybody? So, let's go to the next example. All right. Obviously, we are using the trigonometric functions and trigonometric function formulas at the same time in conjunction with the quotient rule, where we take the top to be the f function, let's say, the bottom to be the g function. So according to the formula that we have, okay, and again, by now, I hope you have learned the quotient rule. F prime, that means the derivative of the top. 1 plus sine x simply gives us cosine x times g times the bottom. Minus g prime, the derivative of the bottom is 1 minus sine x times the top, which is 1 plus sine x. The top is over, the bottom, just write it just the way it is in the parentheses and square. Okay. Now, this one will be distributed, we know that, but what happens here, and it's important to see, a minus b, a plus b is a squared minus b squared. So this parentheses, the 2 at the end gives us 1 minus sine squared. So we are distributing the first portion, and then the last one we do the same thing, gives us 1 minus sine squared. Now what is 1 minus sine squared? It's cosine squared. So therefore, cosine squared and minus cosine squared cancel each other. And that's the final answer, everybody. That is our final answer. Okay. Okay. Let's look at more examples. We're going to repeat the same thing using the quotient rule. Using the quotient rule. Again, let's say this is the f function. This is the g function, so we want f prime g minus g prime f. The derivative of cosine is negative sine times the bottom, minus the derivative of negative sine x is negative cosine x times the top. So please understand, because of this negative sign, you get this negative sign, okay? So with that being the case, you just distribute and observe. It's a simple case, okay? When we distribute, the top becomes minus sine x times 1 is minus sine x, minus plus sine squared plus cosine squared. And these two cancel out, and they give us just positive 1. Sine squared plus cosine squared is 1. So the numerator is 1 minus sine x. Please understand, the numerator is 1 minus sine x. So one of the 1 minus sine x in the denominator goes away. So again, the numerator here is minus sine x plus 1, or simply 1 minus sine x. Okay, everybody? The numerator is 1 minus sine x. And that's why they cancel each other. One of them goes away fast, okay? Simple. Okay, we are repeating the same concept we learned in the previous section as far as the quotient rule and the product rule is concerned, but we are applying it to trigonometric functions. Here's an example we have seen, finding an equation of a tangent line. We've seen this, nothing brand new. How do you find it? You need a pair. The pair is given, or you can say even x is 0, so you can plug in. I hope you see if you plug in, You get e to the power of 0, which is 1, cosine 0, which is 1, 1 times 1 is 1. That's how you arrive at it. Now, the next thing is to find the slope. To find the slope, you need to differentiate. And to differentiate, it's the product rule. So it's a product of e to the power of x and cosine x. It's a product of e to the power of x and cosine x. So e to the power of x gives you e to the power of x times cosine x, plus cosine gives you negative sine times e to the power of x. You can factor out the e to the power of x to make life a tad easier. This is f prime of x. What is the slope? You just plug in 0 and m becomes f prime of 0. Okay. Let me just quickly show you. F prime of 0, that means here change x to 0. So e to the power of 0 times cosine of 0 minus sine of 0. So this is e to the power of 0 is 1, cosine 0 is 1, sine 0 is 0, the answer is 1. That's how we get 1. And y equals mx plus b can be used simply because, and I want everybody to understand why, because the given pair 0, 1 is the y-intercept. The given pair is the y-intercept, everybody, otherwise you can't. And so simply put, that's your b. Okay. Let's look at the next example. We are going to look at y or tan x, and we want to, let's look at it. We said the derivative of tan is secant squared, right, class? Let's prove that. Okay, everybody? Let's prove this is the case. I hope everybody understands what we are trying to do. We are looking at the function y equals tan x, and we want to prove the derivative is what we claim it to be, which is secant squared. Okay, class? We want to prove that. Okay, let's do that. How do we do that? Quotient rule. Quotient rule says f prime g minus g prime f over g squared. F is the sine function. The derivative of sine is cosine times cosine times the bottom, minus g prime minus the derivative of cosine is negative cosine times the top. I'm sorry, negative sine times the top. So minus sine times sine. So the top is cosine squared minus minus plus sine squared, which is 1. So the numerator is 1. What is 1 over cosine squared? Well, we know that secant is 1 over cosine. So 1 over cosine squared is secant squared. And this is the proof, believe it or not. I highly recommend you try cotangent x on your own. We are going to look at the secant x as well. So y equals secant x. Okay, we want to prove this, everybody. And to prove that, we know secant is 1 over cosine. Therefore, it makes sense to use the quotient rule on that again. Very, very simple. I hope you see what I'm talking about, class. So having said that, let's look at y equals secant x and do the quotient rule on that. So simply put, f prime g minus g prime f over g squared. All right. So this is your f, this is your g. The derivative of the top is 0 times cosine x minus, okay? The derivative of cosine is negative sine x times 1 over cosine squared. So what do you have at top? Sine x. What is sine x over cosine squared? Well, we're going to use the identities and how we prove the identities in basic trigonometry. Okay, remember what we want to get, and I'm just showing you. We are claiming it's secant tan, so rewrite this as what? 1 over cosine and sine over cosine. 1 over cosine and sine over cosine, and that's a proof that it is what it is, which is secant tan. I hope everybody's comfortable with that. It really can't get any easier than that, okay, class? So that's a proof. And I highly recommend you try what? You try the cosecant x on your own. So I want to make sure we know what we have done. We looked at the proof for tangent. Okay, class? You do the cotangent on your own. Okay. We did the proof for secant. Now you do the cosecant on your own. You need this practice, and it's very simple. Just mimic what we did here. Cotangent is cosine over sine. Cosecant is 1 over sine, and do the math, and you'll see how easy it becomes, okay? So I hope everybody's comfortable with that. Try this on your own. Here's the next example, and we are going to use the quotient rule. Now, sometimes this stuff involving trigonometry, they become really, really simple. Okay, and remember in trigonometry, many times in order to prove identities, we went from whatever that was given to sine and cosine in many instances, just for the sake of argument. You could do this here, but if you stick with it just the way it is, f prime g minus g prime f. F prime, the derivative of the top, minus secant, okay? It's minus secant x tan x times tan x, minus g prime, the derivative of tan secant squared times the top over the bottom square. And as long as you have this, the rest is pretty straightforward. Okay. Now, first of all, if we multiply this, there's a lot of secant. I hope you see that. I can factor out the secant. And if it helps, let's show you something. If it helps, you can write this portion as minus secant squared, okay, plus secant cubed, if that helps, okay. In any event, or secant cube minus secant squared, anyways. Now, if you take the secant out, let's see what happens. Okay, let me use this to show you. If we take the secant out from here, we have a negative sign, we have a tangent and tangent, we have negative tan squared. Now from here, secant cubed gives you secant squared, minus secant squared gives you minus secant x. I hope everybody can see how we did the factoring, okay, class? Now, remember Pythagorean identities. So remember this one, tan squared plus 1 is secant squared, okay? Now, if I take the tan squared to the other side, and let me maybe write that for you. So if I move this, I can get 1 equals secant squared x minus tan squared x, which is precisely this one. Okay. And this is as simple as it gets. If you want to get rid of secant and tangent and go to sine and cosine, you can. Secant is 1 over cosine, tangent is sine over cosine, and but it doesn't get any more simpler, okay, class? But that can be done. Sometimes there are ways to make it more simplified. Sometimes you don't have it. So this is as good as it gets. Again, a lot of trigonometry involved. I hope everybody is comfortable with that. Okay. Okay. I think we are ready for the next one, class. Okay. Again, we are looking at the quotient rule. So f prime g minus g prime f over g squared. So let's take a look at it. We have sine t at top, everybody. Okay, let me use my pointer here. Sine t, the derivative is cosine t times the bottom. Minus, the derivative of the bottom is simply the derivative of tangent because 1 becomes 0, right? Tangent gives us secant squared times the top, and we write that. Now, remember, I don't fuss about the bottom, simply put it in a parentheses and square it and keep it intact until the end. All right. Let's distribute. So cosine t plus cosine t tan t. Let me just write this at top of this class. Okay. We get here cosine t, right, class? Cosine t plus cosine t tan t, and this is the same as sine, okay? Now, if you didn't change this one, class, that's fine. It's really not that big of a deal because it doesn't really simplify a lot. However, if you change it as secant is 1 over cosine and secant squared is 1 over cosine squared, okay, then you can write this as tangent and secant. I'm not too sure if it really makes that much of a difference, but I'm going to quickly show you what I mean by that. The bottom line is this piece will change to this. Does it really matter that much? Probably not. How does it change? This is sine t, this part, okay, is, I'm going to write it here. Sine t over cosine squared. I'm looking at this part, sine t over cosine squared, okay? And we can write this as sine t over cosine t times 1 over cosine t. And that is what you see here. Does it matter? Since it really doesn't help and it doesn't simplify anything, you don't have to do that, and that's fine. What you need to do is this. Tan x cosine x changes to sine. This one, which ultimately resulted in this one. This you should do. Okay, but the other one is not really that big of a deal as far as I'm concerned. All right, let's look at the next example, class. X squared sine x tan x. Using the product rule here, what matters is you need to understand it's not just f and g, you have 3 functions. So how do you deal when you have more than two functions? You have to cut them into two somehow. Even if you have 8 functions, you can say 4 and 4, okay? And then work on it. Okay, so now you really have the first one. Let me, okay, x squared, okay. That's your first function f, let's say. And this is your second function, the g function, okay. So you take the derivative of f, you multiply it by the brackets, you take the derivative of the brackets itself requires the product rule times x squared. So let's do that, okay? So just to make sure everybody can do this, it's really not that big of a deal. X squared gives you 2x times the bracket, 2x. Now what about this one? Sine gives you cosine times tan plus tan gives you secant squared times sine. The whole thing in some sort of a bracket times x squared. So take a look one more time. X squared gives you 2x times the bracket. The bracket gives you this one times x squared. And this is the only calculus step. I hope everybody is comfortable with that. This is your only calculus step. Now, it's just a matter of distribution. Let's do that. So what do we get? 2x sine x tan x. X squared cosine x tan x. X squared secant squared sine x. And we showed cosine and tan, their product is sine. Everybody remembers that, right? We showed that. Because all you have to do, replace the tan with sine over cosine. And so you do that. So that thing changes to sine x. And when that happens, you can factor out not only x, you can even factor out sine x. So again, cosine x tan x, that's something I hope it's obvious it has to be changed, okay? And then when you change it, x is in common, sine x is in common, and it will look like this. It's pretty simple. Okay, again, we are looking at a lot of trigonometric identities. We are refreshing everyone's memory about those. You gotta get comfortable with. Okay. Same thing. We want to find the equation of a tangent line again and again and again. We need a pair. A pair is given. Fine. Now again, if by any chance only this one was given, you would plug in. You get pi plus tan of pi. Tan of pi is just like sine of n pi is 0. So it becomes pi comma pi. That's one. So let's take the derivative. Y prime. X gives you 1. Tan gives you secant squared. That is not the slope. Becomes a slope if we plug in pi. So m is y prime of a pi. 1 plus secant squared pi. And I hope you remember that secant is 1 over cosine. So 1 over cosine squared x. Now you replace it with pi. Cosine of pi is negative 1. When you square it, you get positive 1. And so y minus y1 equals m times x minus x of 1. Okay, so it's pretty straightforward. We have 2x minus 2 pi. We add a pi and we get 2x minus pi. I hope that's straightforward. And that's the equation of a tangent line. Okay. For function y equals x plus tan x at pi comma pi. That's the answer. All right, we want to look at some limits, okay? And see how we simplify them. Starting with this, the limit of sine x over sine pi x as x approaches 0. Okay. Now notice what we have here. Okay, let me just. We have these two that we have proved. So as we look at this one, seems that if we somehow use this one, we can get to the answer. Okay. Now, what I want you to notice is that the argument of sine, the denominator and this, they must be identical. And when theta approaches 0, becomes 1. For example, I can say, I can replace the theta with x. Are you with me? The limit of sine x over x as x approaches 0. So that's the concept. Okay. So when we see that, okay, we have to come up with some sort of a methodology to do the job. Okay. Notice if I plug in 0, I get sine 0 over 0, sine 0, which is 0 over 0, and it's indeterminate, so we have to use some sort of a technique to do the job. Okay. Now, one is sine, one is theta, so this is not going to work out. So why don't we divide the top and the bottom by the same thing? And when you look at theta, if we had x, that would be fine. So let's divide by x, the top and the bottom, and separate them. In other words, the limit was limit of the top over the limit of the bottom. Okay. Now, when we separate them, notice the top is fine. Look at this one. And you see that the pi x, okay, it's almost like that pi is missing. So look at the manipulation we are going to use. So the top one is fine. You're looking at the limit of the bottom. Again, if this was identical to this, that would be the reciprocal of that. By the way, the reciprocal of that is also 1, but you have to prove that. Again, let me write that in fact for you. So you should be able to show on your own that the limit of theta over sine theta as theta approaches 0 is 1. You should show that. We haven't shown that yet, class. But I hope it's obvious the reciprocal works out the same. You can try it on your own. Okay. And so here's what happens now. Notice what we do. We separate the top from the bottom. This is sine pi x. And the bottom has pi missing. So if I put a pi here, I have to put a pi. Please understand, I can cross out and I get the same expression as here. Why are we adding pi? Because we want this to be identical to this. And by the way, when x goes to 0, pi x goes to 0. Pi x goes to 0. Because x goes to 0 is the same as saying pi x goes to 0. Okay. Now this pi, I can take it out and put it here. Now pay attention to what happens. First, the numerator is unchanged. And look at this. X, x, x. Now look at this one. The pi came and sit in front. Came out. Pi x, pi x. Now this one wasn't pi x, but it was x. Can I change it to pi x? Yes. How? If x approaches 0, pi times x also approaches 0. Now, this pi x and pi x and pi x, they're all identical. You can change them to theta or don't. This thing goes to 1, this thing goes to 1, and you get 1 over pi. This is a page. I highly recommend you spend some time on it to get comfortable with it. Okay, class? You need to spend some time on this just to be on the safe side. Okay. Okay, spend some time, everybody. See the manipulation we used to come up with the answer. So it's a question worth looking at it again. So here's the next one. I'm sorry. Here's the next one. You plug in. If you plug in class, cosine of 0 is 1. 1 minus 1 is 0. Sine of 0 is 0. 0 over 0. So we need to do something about it. Again, we divide the top and the bottom by theta. And we separate them into two limits. This is pretty straightforward. So the top goes to 0. The bottom goes to 1. 0 over 1 is 0. So I want you to distinguish between 0 over 0 and 0 over 1, two different things. Okay. Now look at the last page, everybody. The limits that we are working on, you really want to spend some time getting comfortable. All right. What's happening here? It seems like we have this one. Okay, so the moment you see that, compare it to this and say how we can make this one and this one and this one identical. First, this is x squared, we can say x and x. And then this is number 3, so we need number 3. This is number 5, we need a number 5 here. And you can undo it. So see how we do this. Take a look. Take a look at how we do that. First, sine 3x is here. X squared is x times x. Okay, so look at this one. This hasn't changed. What has changed is this. This one has number 3x. And this is the argument of sine, and you cannot change it. Okay, this has to stay the same. The denominator must look like it, so you add number 3. That means you're multiplying. And you do exactly the same thing. Now look at this part. Sine 5x over x. Because this is sine 5x, you need 5. So you multiply by 5 and you multiply the top by 5. I hope everybody can see what I have done. So one more time. Separate the bottom into x times x. So that's x times x, okay? Sine 3x over x, sine 5x over x. And then because this 3x can't be changed, you have to change the denominator to 3x. How? Multiply by 3. So you have to multiply by 3. Understand they cancel each other, but we want to keep it. Same thing happens with that. Now this 3 comes out, and this 5 comes out, and this x changes to 3x for this one, for 5x to that one. So take a look at what I've done. And I want you to pay attention. Because x is approaching 0, I can say 3x or 5x or 10x or anything like that. Any number time x approaches 0. What happens in this case? Look at this one. Identical to this one, identical to this one. Let me use this. It's important that you make sure this, this, and this are identical, class. This, this, and this. That's the meaning of theta, okay? And so practically you're done. The answer is 3 times. Remember, each one goes to 1, each limit. So 3 times 5 is 15. Okay, class. Here's the next one. You want to find the limit of cosecant x, sine of sine x as x approaches 0. Okay. And by the way, class, it's important to see that this is sine of sine x, sine of 0 is 0, sine of 0 is 0. So this part is 0, this is cosec. So in other words, you get cosecant 0, sine 0. Sine 0 is 0, but cosecant is 1 over sine and it approaches infinity. Depends upon 0 coming from the right or left. So that's why you really have infinity times 0, which is indeterminate. You have to do something about it. So cosecant is the same as 1 over sine, identical to this. So now what you need to see, look at this one, sine theta. So this one, and this one are the same. So this is sine x, this is sine x. So these two are the same. And because x goes to 0, sine x goes to 0 also. So x goes to 0, sine x goes to 0, and we are going to represent sine x with theta. So if this is theta, and now we're going to say this is sine x approaching 0 or theta approaching 0. I hope everybody is following what I'm doing here. This is important that you understand that the argument of sine, the denominator, and what you see here that is approaching 0, they must be identical. In this case, these two are identical, but understand because x approaches 0 is the same as saying sine x is approaching 0. So this really should be changed to sine x approaching 0, and then this is the result. And of course, this is equal to 1. But the given was infinity times 0. This was cosecant, infinity, and this was 0. And again, we are approaching 0. Okay, so it depends from the right or left. How about this one? When x approaches 0, we get 0 over 0. 0 over 0 requires some sort of a work. And here's how we do the work. This is sine x squared, everybody. You cannot change that. This is the argument of sine. So we don't have x squared. How do we make this x squared? Well, if we multiply the fraction, the top and the bottom by x, this becomes x squared. When you multiply the top by x, make sure you understand that means sine x squared times x. So you put it in front of it. So sine x squared times x. So now if x is approaching 0, so does x squared. So now you have this x, we take it, you apply the limit to x, you apply the limit to the fraction. Okay. Now, for x approaching 0, for the fraction, because the top is x squared, the bottom is x squared, and x is approaching 0 is the same as x squared approaching 0. This one, and the argument of sine are identical. So this is equal to 1. What is this one? 0. So 0 times 1 equals 0.